Dear student, welcome in this next video of gas carrier handling. And I want to start by referring to a document I put on Blackboard, which might be of use when we start with the online courses. As I mentioned at the beginning, I will organize next week and then the last week of this module a short online session where we will use this line plan. So the goal is that you better understand the operation I will describe in the next video, where we will start preparing the tanks for the loading operations. So this is a line plan of a mid-sized gas carrier, which we will use during that session. So I would like to ask you to take a paper print of this, at least, let's say, 5 copies. And each copy you should cut longitudinally and make one long stroke of it. You will see that this part, namely that part of the compressor room, the aft part of the compressor room, comes back here again. Yes, this is the same part. So somewhere here, somewhere, they should align. So that means you have one long stroke then of paper, being this tank 1, the compressor room, tank 2, the manifold, tank 3, with all the lines that we will color. So prepare also some items to color the lines, especially red, yellow, purple is used also, and then blue for the condensate or something like that. So please prepare that for the live session of next week. I will communicate the exact hour and place by Blackboard. So you find this document on Blackboard also. It's named Line Plan. Okay, that's just as an information. Then back to the course where we stopped. So we stopped here, if I remember well. And today we will speak about the boil-off control on board of the different gas tankers. For the boil-off control, there are 2 options. The one they use on board of many LNG carriers, namely they use the boil-off gas for all propulsion purposes, so it's sent to the boilers and then used for propulsion. Another possibility is to send the boil-off to a reliquefaction plant where this gas is reliquefied. There we have direct cycle system and the indirect cycle system, where we will go into detail soon. There is a third option which says venting to atmosphere, but this is not an option. This is only an option in case of emergency. For the safety of the vessel, the safety of the crew, you can vent to the atmosphere. But in all other circumstances, this is prohibited since the 1st of January 2016. Okay, so you know that our tank is filled completely with cargo. That means 100%, although most of the time when a tank is loaded, it's about 98% of liquid and 2% of vapor. But during the voyage, heat is penetrating the insulation and evaporating liquid to vapors. That means that the pressure in our tanks is slowly but gradually rising. We must intercept before the pressure exceeds the MAVs, the maximum allowable relief valve setting, because at that moment the relief valve will open. So we must do something with this boil off, and we must avoid to reach this maximum pressure. And therefore we have this system of using the boil-off for propulsion and the system of the reliquefaction plant. First, the LNG boil-off control. For the LNG boil-off control, we have in the machinery room, where the vaporizers are situated, where the compressors are situated, we have a said low duty compressor, LD. We also have high duty compressors, but high duty compressors are used only for cargo operations. The low duty compressor is used to send boil-off gas, heated boil-off gas, to the boilers in the engine room. So the difference between high duty and low duty is, of course, its capacity. This is a low duty, low capacity compressor. It sends the boil off to the boilers in the engine room. Notice also that LNG is lighter than air, and this was the reason why initially, before 2016, before the new gas code came into force, that only LNG was allowed to use as a propulsion. Since 2016, also other gases can be used for propulsion. So, for example, LPG or ammonia can be used for propulsion from now on. And if I'm well informed, next year EXMAR will come with its first LPG propulsed LPG carrier. So an LPG carrier with LPG propulsion. That's what I mean. Good. LNG boil-off control. So we have here at the bottom, we have our cargo tanks. In this case, they are loaded, so they are producing a certain amount of boil-off, which is linearly related to the thickness of the insulation. This boil-off by the low-duty compressor, which is situated on deck in the machinery room. By this low-duty compressor, these boil-off gas are pushed to a heat exchanger, are warmed up till the required temperature, and then are stored in a buffer tank. A buffer tank whereof the pressure in this buffer tank will regulate immediately the capacity of this compressor. And the pressure here depends, of course, on the consumption needed or required by the machinery. Quite an easy system, but not so efficient. There are a lot of losses, and it requires a lot of energy to propel these for propulsion purposes for this vessel. So there are alternatives at this moment, but this is the initial LNG carrier was designed in this way. And there are still a lot of LNG carriers sailing in this way also. Okay, the reliquefaction plant, there the goal is to take away the boil-off. That is the main goal. Since by taking away the vapors from the tank, what you do is in fact you take also away the heat of the tank. Because if there is heat ingress by the insulation and cargo liquid is evaporated, the vapors are containing the heat. Because the liquid is still at its boiling temperature. That does not change. It will remain at its boiling temperature. But the ingress of heat is concentrated in the vapor. So by taking away the vapors of the tank, you take also away the heat. And that is sufficient. What you do then later on with these vapors is not so important. Whether you use these vapors for propulsion purposes or you reliquefy them, that doesn't matter so much. The most important thing is to take away the heat out of the tank. So take away the vapors out of the tank. So theoretically, I repeat, theoretically, sending the vapors into the atmosphere would also be a solution to keep the tank cooled down. but it's not allowed anymore, to make things short. Okay, in this case, gas reliquefaction of LPG and chemical gases, we will reliquefy the gases. Two different types of reliquefaction plants exist, namely the direct cycle and the indirect cycle. In the direct cycle, we will send cargo vapors through the whole reliquefaction system. And finally, this cargo comes back in the tank. In the indirect cycle, we'll keep the cargo inside the tank, and it's an auxiliary cooling system that will cool down the vapor space. Without compressing or using the cargo into a cooling system. Why this distinction between these two different circuits? Not every cargo is allowed for compression or for increase of temperature. VCM, for example, will polymerize at plus 60 degrees Celsius. If you compress the vapors, you will reach a temperature above 60 degrees Celsius, so you will have polymerization. And then VCM, vinyl chloride monomer, will become PVC. And then it will become a block. You will not be able to discharge it anymore. So it is used to make a solid of it, but preferably not in your tanks. So in that case, you will not be able to use a direct cycle for VCM. However, it is possible when you use inhibitors. These are additional products you mix with the cargo in order to prevent this polymerization. But indirect cycle can also be used for extremely toxic products. Because in a compressor room, you have, for example, a lot of connections, and it is almost impossible that there is not one that is a little bit leaking. Now, theoretically, that is not a problem. You got a huge ventilation and so on. And when this ventilation is maintained and set as we discussed, then there is no problem. However, it might become a problem with extremely toxic products. And that is the reason why they say these extremely toxic products, like chloride, for example, must stay in the tank. You are not allowed to take any vapor out of the tank. So this must be carried in a type C tank. And if you want to do cooling of the tank, okay, but then with an indirect cycle so that the cargo can stay inside that tank. All right. I will start with a very simple circuit. And the further we advance, the more elements I will add to this system. And then finally, we will come to a complete working reliquefaction system. As you see, what you see here is simply your refrigerator at home. What we do is we take away the boil-off gas from the tank. This vapor, which here is said to be relatively cold, and indeed that is relatively cold compared to ambient temperatures, but of course this should be reliquefied and come back to the tank as cold liquid. That is what we're going to do. So the first thing we'll do, that cold vapor we bring into a compressor. We compress it so that it becomes hot vapor under a higher pressure. Then we will send it to a condenser which is cooled down with seawater. So seawater is running through this circuit. This hot vapor, let's say at 100 degrees Celsius, enters the condenser is cooled down to, when the seawater temperature is, for example, 20 degrees, then we will come out here with warm liquid at a temperature of plus 25 or something like that. This warm liquid will then be sent through an expansion valve, because here it is still under high pressure. Through an expansion valve, the expansion will take place and the temperature will drop as the pressure drops. So we'll have cold liquid and, of course, still some vapors that we will send back to the tank. This is called the condensate. The condensate, here in the condenser, there is condensation that takes place. So the liquid that is coming from the condenser is what we call the condensate. And that condensate is not only liquid, there's also some vapor. That is called the dryness coefficient of this liquid. It's expressed in percentage of vapor inside the liquid. We would prefer to have here 100% liquid, of course, but that is not possible in practice. Practically spoken, we have here something like 70% of liquid, something like that. And that is the liquid we will send back to our cargo tank, with then some remaining vapors, which of course will come back to the ullage space and that are drawn back up by the system again later on. So closed circuit that can run 24 hours on 24, and that will make sure that our warm vapors here are taken away from the tank. This is what you see on a Mollier diagram. We will discuss that, or you will discuss this in the lapse of gas, the use of the Mollier diagram, but this is our separation between liquid and vapors, and you will have here the dryness coefficients. Here, these lines are the dryness lines, and that indicates here that you'll have something like 25% of vapor inside the liquid. So the first place where we are here is inside the tank. Here we take away the, this should be outside of that, because otherwise there is still liquid inside the vapors, and that is not so good for your compressor. So it should be outside this, on the right side of this bold line. Then we have the compression. Then we have the condenser that takes away the heat. And then we have the expansion, adiabatic expansion tubes till here, where we have liquid again, mixed with 25% of vapors. In this case, at a temperature of -32, so this is for ammonia, as is mentioned here. Okay, we'll add some items, as I declared at the beginning. The first thing we add is what is coming here from the tank is relatively cold vapors. These vapors are at a temperature of, let's say, -20, -25, depending a bit on the ambient conditions, depending on the conditions in your tank, of course, and depending especially on the product you have in your tanks. But it might be that in this vapor, there, because of the cold temperature, of the relatively low temperature of the vapor, there might be some droplets of cargo also. So before we send this vapor to the compressor, we must make sure that there are no droplets anymore inside the vapor. That is why we install a liquid separator. In this liquid separator, the small droplets are filtered out of the cargo vapor, and what is going to the compressor is only vapor, because the droplets will accumulate here at the bottom of the liquid separator, and by the ambient temperature, finally, these droplets will evaporate and can also go to the compressor. So this kind of filter, you can best see it as a filter that stops every droplet of liquid and waits till it evaporates, and then it can go to the compressor as vapor. When you send liquid to the compressor, you know that liquid is incompressible, so that would damage the compressor completely. Then we go to the condenser, as we discussed on the first diagram, and after the condenser, we will first install a collecting vessel, this one. collecting vessel, or also named the liquid receiver. It receives the liquid from the condenser, and it temporarily will stock the liquid inside the drum. So this is in fact nothing else than a drum. You must see it as a drum. But the goal of that drum is just to make sure that here is an accumulation of liquid temporarily. Temporarily, there's a stockage of liquid in this drum to make sure, and that is the goal of it, to make sure that only liquid is going to the expansion valve. Since the goal of the expansion valve is the expansion of liquid. Expansion of gas, that makes no sense. That will not cool down the cargo adequately. So when we have 100% here at the entrance of the expansion valve, our expansion valve, or expansion of the cargo will be most effective. That is why there is directly, that's this dotted line, a liquid controller placed to or set to this collecting vessel. That means this valve, the expansion valve, will remain completely closed until the liquid level in the collecting vessel has risen to this level. When the level has reached this limit, it will automatically slowly open the expansion valve. When the level drops in the collecting valve, the expansion valve will close again. So the level controller will keep always the same level in the collecting vessel by adjusting the opening of the expansion valve. And in that way, we make sure that at the entrance of the expansion valve, there is only liquid. And then that expanded liquid goes back to the tank. So now here they corrected. We have here in the vapor phase, we have the compression, we have the cool down of the vapors by the condenser, the expansion, and then back to there. But the problem is that with one compression, it is only effective when for a factor of 1 to 6. So if you have 1 bar at the entrance of the compressor, you can go maximum to 6 bar. That means if you want to increase that pressure to obtain a more efficient reliquefaction system, or to cool down to lower temperatures, we want to go with this kind of system to a temperature of minus 50 degrees, in fact minus 48 for propylene, you remember from the first course. Then we need several compressions, not only one compression, but several compression. And in this case, we have two compression, a two-stage compression system. That means there are two compressors inside the system. Most of the time, you will find three-stage compression. This is exactly the same as this drawing, only that after the second stage, here thus, we add a third compression. So here you just you add an additional compressor. That's all. That's the only difference between the two-stage compression and a three-stage compression. Okay, what has been added on this drawing is only two elements that we added, namely a drum, and that drum we call the intercooler, and we added this second and maybe a third compression. Yeah, I explained why we added this second and this third compression to keep the efficiency high enough and not to go over this rate of 1/6. So from this first stage compressor, relatively warm vapors are coming out. If we send these directly to the second stage compressor, the gas that will come out of the second stage compressor is far too hot. And that's not good for the cargo, and in some cases it might lead to, for example, polymerization. So to avoid these high temperature at the discharge side of the second stage compressor, we will do an intercooling. An intercooling is a cooling in between the two compressions. And how will we do the cooling? Well, we will cool with the cargo itself, not with water or whatever, not with seawater, but with the cargo itself. So in this drum, this is nothing else than a simple drum, we will expand, this is a second expansion valve, we will expand part of the cargo, and again, a certain level will be kept all the time by this level controller, the dotted line. So we have cold cargo, or relatively cold cargo, inside the intercooler the whole time. Of course, this is only a partial expansion. This is not an expansion to the pressure of the cargo tank, but this is an expansion to the pressure of the discharge of the first compressor. If we go to the Mollier diagram, we see here the first compression, and this is the intercooling at a pressure which is above the tank pressure, but which is lower than the second discharge pressure, of course. So this intercooler is partially filled with cool liquid. So our hot gases coming from the first compression are brought to the bottom of this intercooler. They will bubble up through this cold liquid and come here as a relatively colder vapor and can be sent to the second stage compressor. Here we'll have an increase in pressure again, and that makes it easier for the condenser to reliquefy the vapors. Warm liquid to our collecting vessel, liquid receiver, and then part of the cargo goes to the intercooler, but the remaining part, since we have here cold liquid available, well, we'll use it a second time and we'll send it through these small tubes, this heat exchanger. This is a heat exchanger. We send it through these small tubes of heat exchanging, and we cool the liquid a second time in the intercooler before sending it to the expansion valve. So after the condenser, where the liquid comes out at something like 20 degrees, depending on the seawater temperature, we have a second cooling from 20 degrees to a lower temperature. And in fact, that is what we will do before the expansion. That is, normally the expansion was here. Thanks to the passage through the intercooler second time, we have this additional cooling. And the result is that we arrive here with the liquid in our tank. So that means that our dryness factor, which is situated here somewhere, will be lower. So there is more liquid sent to the tanks and less vapors thanks to this additional cooling in the intercooler. So that is more or less the principle of operation of a 2 or 3 stage compression reliquefaction unit. This I explained. Now, on some systems, you have an additional condenser. What will happen in our condenser? This is our main condenser, which is fed with seawater, as on the previous drawings. What can happen here in this condenser is that your cargo will condensate, no problem. Your liquid is sent to your liquid receiver, but it might be that there are some impurities in your cargo, especially when you come from another cargo. What are these impurities? Well, it can be nitrogen, It can be oxygen. And they will not liquefy under the conditions of the condenser. They will only accumulate in the condenser. So after a while, after a number of hours running of this system, all your oxygen and all your nitrogen will accumulate at the top of your condenser, and the pressure will increase, the efficiency will decrease. What you can do then is release the pressure in the atmosphere, but of course with the risk of sending also cargo to the atmosphere. And that is the reason why we use a purge gas condenser. So what we do, we will send our gas, liquid, after the expansion valve, not immediately to the tanks, but we first pass through the purge gas condenser and then to the tanks. So this is the cooling liquid for your purge gas condenser. It's the cargo, in fact, which you send back to the tanks. On the other hand, we send a small amount of the upper part of our main condenser, these vapors, we send through this purge gas condenser. This purge gas condenser, which is now cooled at the boiling point of your cargo. So if there is any cargo left inside these vapors we send to the purge gas condenser, they will definitely condensate here. By a small pump, we send the condensate to the tanks. Everything which is not condensating in the purge gas condenser are impurities. It cannot be cargo, impossible. Under these conditions, that means with an increased pressure and the temperature of the boiling point, all cargo will condensate, for sure. So everything what is not condensating here are impurities and can be sent to the vent riser. Normally, this is a fully automated system, and this is a system, a valve that will open depending on the pressure here inside the purge gas condenser. If it goes over a certain limit, it will open automatically, and these impurities will be sent to the vent riser. So with the purge gas condenser, you can separate cargo from impurities, which you cannot do with the main condenser. All this I explained. Second direct system. So this is what we've seen. We call it the two-stage or the three-stage reliquefaction unit plant, whatever, depending on the number of compressors we will use. The one-stage compressor unit does not exist. It will not work. You need two, at least, or three-stage compressor. With one stage, that will be insufficient. Beside this two or three stage compression, there is also what we call the cascade system. And a cascade system you will find on larger LPG vessels, since its efficiency is better and it is relatively independent of the seawater temperature. The problem of the previous system, and I'll go back for a minute. The problem of this system is that it depends a lot on the maximum seawater temperature. When you need this system, or when you have this system on board, your ship is equipped with this system, and you need to go to the Persian Gulf, well, I wish you good luck. As chief mate, you blood. Since this system is designed for a maximum temperature of seawater of 32 degrees. Now in the Persian Gulf, you know that temperature, the average temperature is 32 degrees. That means the new system will run, but after a while, some hoops inside these condenser will be blocked. And so the capacity will decrease, and therefore you will have a lot of alarms when this system is not operating with a temperature of 32 degrees. So that will give you a lot of problems. I speak from experience here. And therefore, on larger LNG LPG carriers, we use the cascade. It is more efficient. The cost is maybe a bit higher. I don't know. I don't have to pay that. But the cost is maybe a bit higher, but it is more efficient and it's less depending on the seawater temperature. In fact, the system is very easy. It are two identical systems. So remember the first system I showed you, the one-stage compression. Well, that one-stage compression you will find here: cargo vapor, liquid separator, compressor, cargo condenser, expansion valve, back to the tank. Mention here that the collecting vessel or the liquid receiver is incorporated in the cargo condenser, so that you send all liquid to the expansion valve. Now, the big difference with the previous system is that a cargo condenser is not cooled by seawater, but is cooled by a refrigerant. And here is mentioned R22, but I'm very sorry, I didn't took it away, but R22 is forbidden, cannot be used anymore, and you know the reason why that is. So, okay. It seems that I am gone at this moment. What is that? Okay, here we are. So that means that we are not cooling with seawater, we are cooling with another refrigerant. This refrigerant can be, for example, R417. This can be ammonia, this can be propane, for example. All that is possible, but it should be a replacer of Freon, of course. Freon is not allowed anymore. I should delete that, but that has not been done. I apologize for that. But for the rest, it is exactly the same system, this refrigerant system. So what is coming out here are warm vapors coming from this cargo condenser. And these warm vapors are sent to the cargo liquid, to the refrigerant liquid separator here. And then it's exactly the same system. So they're sent to a refrigerant compressor, to a refrigerant condenser, and in that condenser, we use, of course, seawater. That condenser, we use seawater, and then the refrigerant liquid is sent to the collecting vessel, exactly the same as with the cargo, to an expansion valve, and then we have cold refrigerant. That cold refrigerant we will send to the cargo condenser, and then the system is closed. So we have two identical systems, one where the cargo is circulating, the second one where the refrigerant is circulating. And you see we have on the Mollier diagram two exactly the same cycles. But of course, on two different Mollier diagrams. This is the Mollier diagram of the cargo, this is Mollier diagram of the refrigerant. A very easy system, but excellent operating system, which has a very high efficiency and which is much easier to use than the three-stage compression, for example. Much more stabilized. All right, that for the LPG or chemical gases reliquefaction units. But more and more, because we need to increase efficiency of these gas carriers, more and more we find reliquefaction units on LNG vessels. Since the system we used to use, namely using the boil off for the boilers and then to propulsion or turbines, gas turbines, that is not so efficient. And in times that we have to save money, well, we need to find for solutions. And one of the solutions, and that has been especially invented or drawn up by Moss. You remember the name Moss maybe of these spherical B tanks, spherical LNG tanks. The Moss system, they are really doing a lot of research to this reliquefaction on board of LNG vessels. System used is a system with nitrogen. The boiling temperature of nitrogen is minus 196, so it is lower than LNG, so it can be used to condensate LNG. Of course, you can imagine if the boiling temperature of nitrogen is minus 196, that you'll need a lot of energy to reliquefy the LNG. And that is one of the cons of the system. And that is why we were not happy to do so. But finally, we try to create systems that can do it on an as efficiently possible way. And this is the system, this is the standard Moss system. And I will only explain this one because you will see there's another one in the course which is quite equal to this one, but you only need to know this one or to be able to explain this one. Okay, for the cargo, it's quite easy. The system is quite easy. You got the boil off from the tank, boil off gas feed from the tank at the tank temperature, which is more or less minus 160 for the liquid. The vapor, as you see here, will be minus 145, 150, something like that. That gas is then compressed to 4.5 bar by a double compression. You will have a compression here, up, you'll have a compression here to 4.5 bar. The boil-off gas under compressed condition will then pass through a first condenser, heat exchanger, and then go to a second condenser for an additional cooling, where it condensates and then will go to this collection vessel. And then when it is liquid, you see here the level controller dotted line to the expansion valve, exactly the same as in the previous examples. And that will go to the tanks, of course. So cargo-wise, it's very easy. Now the green lines are the nitrogen lines, is the nitrogen system. For the nitrogen system, there are 3 compressions and 1 expansion. So here is our motor that drives the 3 compressions. So we'll have warm vapor, warm nitrogen vapor. No, not warm, cold, sorry, relatively cold. Nitrogen vapors coming from the condenser. These vapors are compressed a first time, and then we reach already almost 100 degrees already. So that's quite hot. If we compress that immediately a second time, we will have temperatures which are not allowed for the nitrogen. So what we do after the first compression, we pass through a heat exchanger and we cool down these nitrogen under the pressurized conditions. This cooling is done with ordinary seawater. After the cooling, we go to a second compression, Again, we will have here very high temperature. So before we can do a third compression, we need to cool down again. Okay, we do the third compression. We have high temperature, so we cool down again. We are now at a pressure of 57 bar. So after the three compressions, this is from 1 to 6 bar, this is from 6 to 36 bar, and this is from 36 to 57 bar. For example, I don't know exactly how it is, but it's not more than 1/6, as you can see. This 57 bars at a temperature of something like 40-50 degrees is then sent to the heat exchangers, to the condenser. So the nitrogen is cooled here by the nitrogen which is passing in that way, where we come later on. So here, this nitrogen goes into the condenser for additional cooling. It comes out of that condenser at a temperature of -110, -120, something like that. Then it goes to an expansion, and that expansion is the propulsion for the third compression. That is the reason why it is connected here. So we go to a connection, to an expansion from 57 bar to 14.5 bar. After that expansion, we have nitrogen at -160, -170 degrees. And that goes to the first heat exchanger, to the first condenser, where our cargo, after it's pre-cooling here, is now cooled to -163, to this boiling point. So here, in the first stage, our nitrogen will take heat from the cargo, and when it's warmed up, it will go to the second part of our condenser, where it will cool down with the remaining cold. It will cool down our nitrogen, and it will cool down for the first time our cargo. What is remaining here are then hot, relatively warm, not hot, relatively warm nitrogen vapors that can be sent to the first compression again. But of course, you'll need to go to much higher pressures. For 57 bar, let's say that for the LPG compression, you go up to pressures of 12 bar, depending a little bit on the product you are carrying. But for ammonia, something like 10, maybe propylene might be a bit higher, 12, 13 bar. But here for LNG, you need to go up to 57 bars. That's quite high. Okay, so as I mentioned, this is exactly this, no, not exactly, but more or less the same installation. The only difference is that this has been specifically designed for a Mark III concept. So related to capacity and pressure, this might be a bit different relate to the previous one, but you only need to understand and explain me the standard Moss reliquefaction plant. If ever I ask you this system, I will give you the drawing and you explain me how it functions, just as I explained to you now. All right, so more and more LNG vessels are sailing with a reliquefaction plant because there is the problem of this capacity. The increasing capacity will create, of course, also more boil off. Where do we go with this boil off when the ships are sailing at slow speed? Huh? That is the problem. So that is one of the reasons why we need reliquefaction on board of LNG vessels. Another reason why is that we go more and more for alternative propulsion. For cost reductions, of course. Depending on the price of the fuel oil related to the boil off, to the price of the gas, it is possible to sail one day on fuel oil and another day on boil-off gas, whichever is cheapest. That is an option that was not possible before. But with liquefaction plant, you can say, okay, this week I'll sail on fuel oil, and next week I'll sail maybe on gas when the price of the gas has dropped. So we have different possibilities, alternatives for LNG carriers relating to propulsion. We have a slow speed diesel with boil-off gas liquefaction. We have a dual fuel diesel electric propulsion. We have the gas turbines, the classic one. And we have a combined cycle electric propulsion, and even others at this time that exist. So the traditional system or diagram for the operation of an LNG carrier could be as this one. So this is in fact how an LPG carrier is working, but you can copy that, of course, to an LNG. You have a fuel oil system that is used for a slow speed two-stroke diesel engine. And you have fuel oil for the generators. Generators are producing electricity. That electricity is used for the liquefaction plant, and the liquefaction plant is used for a closed system to treat the boil-off gases. That's the traditional system we use on board of LPG carriers, and which can be copied, of course, to LNG. Another possibility is that you have a fuel oil system. I will go to dual fuel engines that generate electricity that can be used for an electric motor. And here you have the option to choose fuel oil or boil-off gas. You know that when there is not sufficient boil-off gas available, that you have the low-duty vaporizer available to create yourself additional vapors for consumption in case you want to sail on gas. So this is a diagram of diesel electric propulsion system. Okay, that for the LNG systems. Now I just want to add a small word on the compressors themselves. So the compressors are, of course, increasing the pressure, but we have different possible systems. The first one is this reciprocating oil-free piston type. The second one is the screw type. The reciprocating system means that the piston acts in both directions. So it is compressing in the upward movement and it is compressing in the downward movement. So here, in fact, you have the suction of the first stage. You have the discharge of the first stage. The discharge of the first stage is connected with the suction of the second stage. And this is then the discharge of the second stage. So you have two stages in one compression, in one compressor, sorry. And this is the compressor that you will find in the in most of the two-stage compressor units. Here you see the complete system with here the compressors, 1, 2, 3 compressors, with here the condenser and here the intercooler. So horizontally is the condenser, vertically is the intercooler. The motor is here. This is the motor that drives through this axe here, the compressors. And that is the reason why you see that this picture has not been taken on board of a vessel, since this picture, motor, where's my, here, motor and compressor are in the same room. And that is not allowed on board of a gas carrier. This plate here is an indication for the bulkhead that separates the motor room from the compressor room. Remember that in a motor room always is a positive pressure, while in the compressor room always is a negative pressure. So it is impossible that motor and compressor are in the same room, as we learned before. But this is an installation which is ready to be installed on board of a vessel. Here another diagram of a system where you see also motor bulkhead, then here to the compressor. Okay, the second type of compressors, and this is mainly used in the cascade system, because in the cascade system you don't need these high pressures because your cooling is better. There we will use the screw compressors. So screw compressors are just screws running at high speed and pushing the gases to one direction. Then we have the dry and the oil flooded screw compressor. The difference is that in the dry compressors, the distance between the rotors is a bit, between the lobes is a bit higher, but the number of revolutions is higher also. Number of revolutions per minute is higher also, in order to have a higher efficiency. Advantage, of course, is that your cargo is not mixed with oil. In the oil-flooded screw compressors, the lobes are placed almost one against the other, so there is no space that gas can escape. So these can run at a lower RPM, but of course you need to inject oil also to keep it lubricated. That means that your cargo will get mixed with oil. So after compression, you need an oil separator to remove the oil again from your compressed cargo. Now, theoretically, that's not a problem, but of course, it might be that some of the oil is still left inside the cargo. And this is often the case when you gas-free cargo, when you gas-free a tank, that at the moment that the tank is back under air and you want to inspect the tank, that you find traces of oil on the bottom of your tank. This can be of your compressors, but most of the time it's from the compressors of the shore. But okay, that is depending on the compressor they have chosen. And then finally, from this reliquefaction plants, the indirect system. So as I explained, in the indirect system, it is a refrigerant system that will cool down the ullage space. Your cargo remains in the tank. So there are two possibilities. One where the cargo is completely isolated inside a tank, and where you have not heating coils, but cooling coils at the top of your tanks. So there's a refrigerant, propane, ammonia, R417, that is circulating in this system. And of course, the temperature of the liquid sent to the tanks is below the boiling point of the cargo, so that the vapors can condensate on the heat exchanger here, and they will fall as droplets inside the tank. What you do is you take away the heat of the ullage, and that is the only goal of your reliquefaction plant, of your cooling system. Another possibility is that you partly send your vapors outside the tank, but your cargo vapor is not compressed, so no increase in temperature, which is very important to avoid polymerization, is sent then to a cargo condenser, and the condensate is pumped back to the tank. Because there has been no compression, it will not go automatically back to the tank. You'll need to pump it. But everything is happening, of course, in this system, in this refrigerant system. So both are possible and are called indirect cycles, since your cargo has not been compressed. Okay. Then there are a few slides regarding the reliquefaction plant operations. This is only for your information. Just go through it, read it, just you know more or less what is inside it. But I will not go into detail for the simple way that it is different for each operation. So that is one of the first things you'll need to do whenever you come on board of gas carrier. That is to read how to start up your reliquefaction plant. Your chief mate will count on you that you are able, after a few weeks, to start up the reliquefaction plant. So please read the manual. And this is part of it, where the procedure is described how to start up the reliquefaction plant. You will do in the labs also a startup of a reliquefaction plant where it is described step by step in detail, and where you will follow closely these indications. But since it is different for each reliquefaction plant, it makes no sense to learn this by heart, but try to understand what I've written here. Okay, that for the reliquefaction plant, and as we know that that third option was venting boil off to atmosphere, that is prohibited since the 1st of January 2016. What a shame, what a shame, what a shame that it took so long, because this means that on the 31st of December 2015, you were still allowed to send these vapors also for the chemical gases into the atmosphere. Okay, since the 1st of January, finally we decided not to do so anymore. The venting of the boil off to the atmosphere can only be done in case of emergency. And this is what happens, of course, when you fall asleep, the pressure in your tanks rise, and your safety valve opens, then it is vented into the atmosphere. But that cargo is lost. Don't forget that. That is a loss of cargo. It's not allowed, but okay, it's for your safety at that moment. But in normal operations, no boil off is sent to the atmosphere. Good. That was it for the boil off control. And that was it for this video. I'd like to thank you very much and hope to see you soon in one of the next videos.